molecular hydrogen gas. It has the most potential in so many conditions. So you're in for a treat because we're going to go into the latest updates with one of the best experts in the world on molecular hydrogen.
Typically, when we hear about molecular hydrogen gas, we think of maybe an alternative energy source because it's 3 times more energy dense than gasoline. And it turns out that although it can be used as an alternative energy source, it can also be used as an alternative medicine, so to speak. In order for a molecule or a nutrient or vitamin to do any good for you in the first place, you have to actually get it inside of the cell. And some of the things that dictate cellular bioavailability is, number one, its size. And the smaller the molecule, the easier it can get inside of the cell. And hydrogen gas, as we mentioned, is the smallest molecule. So it has that, it beats every other molecule out there. We are finding that hydrogen gas is able to suppress or decrease excessive oxidative stress, as well as excessive inflammation, as well as excessive perturbations from normal homeostasis. Hydrogen gas is clearly, its role is much more than just acting as this typical antioxidant, but truly acting as a gaseous signal modulator that is able to influence gene expression, protein phosphorylations, signal transduction cascades, all of these things that help explain the therapeutic effects we're observing from hydrogen gas.
Welcome, everyone. This is Dr. Mercola helping you take control of your health. And today we have a real treat for you. We are joined by Tyler LeBaron, who is the founder of the Molecular Hydrogen Institute and really one of the most knowledgeable people in the United States about molecular hydrogen because of its incredible benefits. And we're going to talk about what some of those are. And Tyler is really the one who helped me understand this and continually contributes to my evolution of thinking on the proper application of this. So welcome and thank you for joining us, Tyler.
My pleasure. Thank you. Yeah, it's always great to have the opportunity to talk about some of the research that I've been fortunate to be involved in.
Yes. And when we last talked, I don't think you were formally involved in your PhD program, but now you are. And because of all the studies that you published previously, you're on an accelerated path and you're going to be having your PhD soon. So why don't you just briefly describe that and then we can go into some of the new science.
Yeah, I've been lucky to be involved in the hydrogen research for quite some time. And of course, I've put off a little bit. I started my PhD earlier because I was going to want to do it in molecular hydrogen. And then I had the opportunity several years ago, and so it's I've been able to really work with a lot of different groups, and especially some of the stuff we're doing right now, and things are going really well, and we're finding some really exciting things that I'm excited to talk about.
Yeah. So you're doing a lot of traveling because you're doing your PhD work in Europe, and you're still taking regular paths back to China, I believe, or is it Japan or China?
Well, China and Japan, yeah. So I collaborate with some different people groups in Japan as well as in China. China more so recently. Well, I wasn't going to say more recently, but now with the coronavirus.
Yes.
Yeah, I haven't. I was there in December, and then I was there at the beginning of the month in January, right before a lot of the outbreaks really started taking off.
Well, the outbreak started in December.
Yeah.
Beginning in Wuhan.
Well, I mean, before they grew so much that the airports were being closed down and everything, because I was right there in Shanghai, and then a couple of weeks after I got back, that whole city became, under like lockdown basically.
Yeah. So, well, I'm glad you made it back.
Yeah, me too.
And we're quarantined out there. So, well, before we begin into some of the exciting research, I think it might be wise to summarize a bit, at least, some of the benefits of molecular hydrogen and why it works, maybe in a few minutes, and how it's a potent selective antioxidant, and unlike typical traditional conventional antioxidants like vitamin C and vitamin E, when taken in excess, can be actually highly counterproductive and really nullify some of the benefits of hormetic stressors that we're put through, like exercise. Whereas hydrogen doesn't have that downside. So, which is one of the reasons why it's my favorite. And I think it's just, there's almost no downside to molecular hydrogen. So why don't you just summarize the the reasons why someone should be interested in this.
Yeah, absolutely. And just to make sure everyone's on the same page, when we're talking about molecular hydrogen, we are talking about the gas, the H2
Mhm.
molecule, just one hydrogen and another hydrogen that they bind together, and now you form the H2 molecule. And typically when we hear about molecular hydrogen gas, we think of maybe an alternative energy source because it's 3 times more energy dense than gasoline. And it turns out that although it can be used as an alternative energy source, it can also be used as an alternative medicine, so to speak. And this molecule also, because it is so small, and it's the smallest molecule in the universe, smaller than oxygen even, it's able to diffuse through the cell membranes, like the blood-brain barrier, for example, the subcellular compartments, into the mitochondria, the nucleus. It's able to get everywhere very easily, very quickly, because it is so small. It doesn't need specific transporters. And that's a critical part to just consider for a little bit. In order for a molecule or a nutrient or vitamin to do any good for you in the first place, you have to actually get it inside of the cell. So this bioavailability becomes one of the major factors in all pharmacology and nutraceuticals and so on. And some of the things that dictate cellular bioavailability is, number one, its size. And the smaller the molecule, the easier it can get inside of the cell. And hydrogen gas, as we mentioned, is the smallest molecule. So it has that beat. It beats every other molecule out there. And then another part is its charge and polarity. Well, hydrogen gas has no charge. And that's very critical, because if it was charged, say like an ion, so just think of, say, potassium ion or a sodium ion, these are very small ions, but because they are charged like this, they cannot go through the cell membrane. They have to go through a protein channel in order to get through the cell membrane. And the other thing is even like water. So water is a neutral molecule. It looks like Mickey Mouse, oxygen, and the 2 hydrogens combined, right? Of course, that's very different than molecular hydrogen, because notice in this case with the water, the hydrogens are tied to the water molecule. So it's totally different. But with that water molecule, although it is neutral, it has a polarity. It has the oxygen has a slightly negative charge, and the hydrogens on the water molecule are slightly positive. That also prevents it from going through the cell membranes, and it has to go through a protein channel called aquaporins. So again, because hydrogen gas is small, it's neutral, and it's nonpolar, that again allows it to enter through the cell membranes and diffuse into the subcellular compartments easier than anything else. So it has truly the best or most favorable distribution properties of pretty much any other supplement or molecule that you could dream of. In fact, that you could even create, if you will. Hydrogen gas is already there. So that's a very important part about the pharmacokinetics and how hydrogen gas can get into the cells. Now, going to some of the benefits, I guess we can talk about just some of those brief things. We are finding that hydrogen gas is able to suppress or decrease excessive oxidative stress, as well as excessive inflammation, as well as excessive perturbations from normal homeostasis. And maybe we should dive into each one of those areas a little bit to describe, to explain why it's important about this excessive that I'm talking about.
Yeah, that's the key point, is emphasis on the excessive, because it only addresses excess oxidative stress, because some oxidative stress and some free radicals are beneficial. Nitric oxide would be a classic example.
Yeah, thank you. Exactly. And maybe many people don't grasp that initially. We just think of oxidation as really bad, which it is, right? Again, we know that when you cut your apple in half, your avocado, right? Yes. But when you have your fruits or different things, you have the oxidation. That's what causes the brown. It's what causes rusting. And the exact same thing really does happen in our bodies as we breathe the oxygen. When we exercise more, we're breathing more oxygen, and that is causing this oxidation. So that's a process always occurring. In fact, that's how we metabolize food, is through the process of oxidation. But that oxidation that is necessary for life to exist is also the very thing that is slowly taking away your life, if you will. So oxygen does have this toxic effect as well. And like you mentioned, I'm glad you brought up nitric oxide. That is, by definition, a free radical, has a lone pair electron. But of course, nitric oxide is one of the most important molecules, similar molecules that there are. It induces vasodilation, and a whole host of wonderful and very critical benefits. And we're seeing other things, including superoxide radical. That also is a free radical, but it's extremely important. So very important that we understand that it's about the excessive oxidative process that's going on. And that's when we get into, well, because we have our body's natural antioxidant systems already, and we have to have that in order to fight against this toxicity of oxygen. So when you look at plants, for example, one of the reasons why we want to eat plants, we get antioxidants from plants, is because plants also developed ways to handle this toxicity of oxygen. And so plants develop antioxidants. And when we eat the plants, we get some of those antioxidants, right? So that's how this process works. Now, that oxidative process, or that oxidation that's occurring, some of the things is involved besides the cell signaling, but also even for protein folding. So when you fold your proteins, you sometimes have to have an oxidative power that in order to get the correct folding of the proteins. This happens in, like, say, the endoplasmic reticulum of the cells. And if your proteins are not folded correctly, they're not going to have the right structure. And that's the fundamental principle of biology and biochemistry, is that structure dictates function. So if you don't have the correct structure, then they're not going to function correctly. And it turns out that aging is often associated with a decrease in this oxidative power, oxidative potential that is required to fold your proteins correctly. And so you actually have a lack of oxidative power going on in the endoplasmic reticulum, while at the same time you're suffering from an excessive amount of oxidative distress that's going on in the body. So that's very interesting to consider, that in the exact same cell, you're having an oxidative distress, maybe in the cytoplasm, as well as a lack of oxidizing power potential in the endoplasmic reticulum. And we can call this a redox dysregulation. And when you have this dishomeostasis of redox meaning oxidation and reduction, when you have this dysregulation, that's really what sets the stage for diseases and aging and a whole bunch of other pathological problems.
Yeah,
So,
and there's tools like hydrogen that can help resolve that, and there's other tools like saunas, especially for the misfolded proteins, which should be particularly beneficial because they create these heat shock proteins, which are particularly beneficial for refolding or removing the damaged proteins.
yeah, exactly. And it's interesting, even like with sauna and different things and exercise, when we do some of these different therapies, whether it be photobiomodulation, exercise, the sauna, a lot of this actually mildly increases oxidation in the body. Mm-hmm. And that oxidation in the body is what induces heat shock proteins. So the production of heat shock proteins is because there was some sort of a damage, a mild damage that was done to the body. And then we get these heat shock proteins, and we call this hormesis. and this is an important word, because we're going to talk about this a lot when we talk about the benefits of molecular hydrogen, because it seems to work through some similar processes of hormesis. So when it comes to the oxidative stress that's going on, we really need to get that back into homeostasis. And we can't just come in and neutralize all the free radicals. So many antioxidants, they contain this, it's called the conjugated pi system, where I just have a whole bunch of electrons that are able to easily donate and scavenge and react with a whole bunch of radicals or oxidants indiscriminately and neutralize them.
And let's give an example of this. Would intravenous glutathione, which is frequently administered in many alternative medicine clinics, would that be an example?
Yes, absolutely. Yeah. Intravenous glutathione, in fact, almost every standard antioxidant that we're aware of can fit into this criteria. And in almost every single case, well, and I say that because there's probably some cases where it's not true, but I can't think of any. When you administer a whole bunch of them for a long time, you end up increasing a dysregulation of the redox homeostasis, because you're causing a too high of a reductive environment, and the cell can't keep up with this, and you start getting problems. Even genetically, when you do genetic mutations to, say, have a constitutively upregulated NRF2 pathway, which we'll talk about later, but NRF2 causes more antioxidants. When you have this, then you end up having a lot of other problems, cardiomyopathies, and this overtly reductive environment in the cells can lead to a lot of problems. So Absolutely. That's why taking lots of antioxidants all the time, day in and day out for years, it simply causes a lot of problems. In fact, they've had to stop a whole bunch of clinical trials because those taking these antioxidants were dying faster than those taking the placebo.
Yeah, there was a common theory of aging. The free radical Darman, I think Darman Hardin is the guy that started in the 50s, and it's become less popular now. But that we're suppressing this oxidative stress with antioxidants was one way to slow down the aging process. And as you just mentioned, the studies don't bear that out.
Yeah, exactly. Now, of course, there are studies in different animals. There are studies in different fruit flies, and there's different things showing that clearly oxidative stress absolutely contributes to aging.
Mm-hmm.
But that's when it's oxidative stress, and that's really what's occurring. Sometimes antioxidants can even exacerbate oxidative stress because they can increase like Fenton reaction cycles and redox cycling and end up being potent pro-oxidants and things as well. So it is very complicated, and we have to be very cautious. And we could even talk about some of those studies like with the vitamin E or beta carotene. Oh, well, those are just synthetic. And that's why they're having these problems. They weren't taking the right form. But whatever way that we want to describe that, the fact is these are still antioxidants in the conventional sense. They're still reductive molecules. They still had a negative impact on the body, and it's possibly because of this excessive amount of reductive character that was going on. And hydrogen gas simply doesn't do that. In fact, that's why hydrogen gas we know can be one of the reasons we know it can be so safe is because it simply does not have the reductive power or potential to neutralize or react with some of these critical, important signaling oxidants, such as hydrogen peroxide, singlet oxygen, superoxide radicals, nitric oxide. It just does not have the ability to react with these, even in vitro. If you just put the two together, they don't react.
Well, and what's the current thought on hydroxyl free radical? Because I think initially that was the consideration that was its mechanism of action. It was neutralizing this free radical, but I don't believe that's the current thought.
Yeah, and that's probably right, because there's so many discrepancies about that. But you're right. Initially, it was considered, well, hey, if hydrogen gas, it can one of the very few free radicals that hydrogen gas can react with is the toxic hydroxyl radical, and the hydroxyl radical is literally the most reactive radical in the body. It is such a strong oxidizing power and potential that it reacts indiscriminately with anything. Instantaneously, and it's so strong, has such a strong oxidizing power that it actually can react with hydrogen gas, and when it does, you create simply water, which can be nice, right? And because hydrogen gas is able to distribute throughout the body so quickly, and because it's so small, then during the times of a trauma, so if you consider say a cerebral infarction, a stroke, where you have these conditions of ischemia, reperfusion, which to talk about that, the ischemia part is when you have the lack of blood flow to, say, your brain, and then that causes lots of damage. Of course, if you don't get blood flow soon enough, then if you have no oxygen and no nutrients, then that tissue, those cells, will die. But interestingly, even more damaging than a short-term ischemia is the reperfusion process, which is when you bring back in the oxygen-rich blood into those cells, into the organ. And when you do that, that creates a cascade of all these oxidative and inflammatory responses, and the sequela of all these events leads to necrosis and apoptosis and death and everything. And that's why, for example, people who suffer from a myocardial infarction or different areas, sometimes they can be resuscitated, and then it's days later they end up dying, or they end up having severe damage because they saved them immediately, but the long-term effects ended up being very damaging. Okay, so this is a critical aspect of how molecular hydrogen could work during these times of ischemia, reperfusion, and other issues, is because during that time there's a whole bunch of hydroxyl radicals that are produced, and the hydroxyl radicals are just so damaging and lethal. And then hydrogen gas, because it has such a small it's such a small molecule and can rapidly diffuse there, then it would react with hydroxyl radicals, prevent the damage, and there you go. And we see the benefits of hydrogen gas appears to almost be doing just that, because that first article that you and I talked about in Nature Medicine and published in 2007, that's exactly what they found when they induced this ischemia perfusion in the brain by cutting the blood supply to the brain, and then they inhaled hydrogen gas. Well, it was a rodent study, right? And they administered 2% hydrogen gas. That 2% hydrogen gas significantly suppressed the brain damage induced by this cerebral infarction, basically. And it was thought, well, hey, that's probably because it's able to get through there where all these hydroxyl radicals are being produced, quench all those bad guys, and now we don't have that damage. But to your point, maybe that's not really what's going on.
Well, but let me stop here, because I think that is an important consideration that you bring up that I seem to have neglected. But it would appear that part of the revised protocol for every heart attack, at least acute heart attack, and stroke should have molecular hydrogen implemented ASAP, because of the reperfusion, ischemia reperfusion injury prevention potential. And has there been studies that looked at this, or are there any protocols being deployed currently? Because it would seem this like the perfect marriage for this. I mean, why would you not do it? That there's like there's no risk. The cost is almost free, and the upside potential is enormous.
Yeah, absolutely. And fortunately, there are some good some research programs that are getting into place with this, because the animal models have been very, very promising. In fact, one study, for example, in a rodent study, just consider these numbers as I tell them, with post-cardiac arrest syndrome, with no treatment at all, there was only a 43% survival, okay? And so that's pretty grim, 43% survival.
Almost 1 out of 2 are dead.
Yeah, exactly, right? Now, when they do the standard therapy, which is therapeutic hypothermia, cool the body down, because that's going to lower the metabolism, and that's going to create less free radicals. So it works very well. In fact, so well that the survival rate goes from 43% all the way to 77%. So that's, obviously that's why it's often done. Now, when they used hydrogen gas, just hydrogen gas alone, that survival rate went to 92%. And then when they combined it, it was 100% survival.
Wow.
Okay.
That's exactly what I would predict. I didn't know the studies were done, but that is just awesome.
Yeah.
And it's almost free. I mean, it just literally costs far less than $1 to implement that therapy.
It's it really is a pretty easy. And now again, that was just a rodent study. There's quite a few rodent studies that are coming out. There's studies that's been done in pigs. In fact, we did some research in Prague last year with inhalation during heart transplants, and we're still analyzing the data, but we saw some good effects, decreasing oxidative damage and things. There was also a study done by Harvard University, published in American Heart Association Journal, and they found some phenomenal effects using hydrogen gas for extracorporeal blood circulation.
Yeah, well, that is just fantastic. I wasn't expecting to find new indication that I hadn't appreciated before, but that is good. But I interrupted you and took you off on a tangent. You were going to explain the believed mechanism now.
Yeah,
the primary mechanism is not hydroxyl, even though it has great benefit in that for these 2 acute problems. And these are not small considerations. Stroke and heart attack are the leading cause of death in the United States, so people know. I mean, this is what takes most people out.
Yeah, that's right. That's right. In fact, well, and I'll get, now I was distracted, but I forgot to tell you the most important aspect of all of this. The Japanese government actually approved the inhalation of hydrogen gas as an advanced medicine for the treatment of post-cardiac arrest syndrome. So now there's a major study going on, 360 patients in multi-hospitals, looking to really determine the true efficacy of inhalation of hydrogen gas during these exact conditions that we're talking about. And so that's going on in Japan, and there's some clinical studies that have already come out showing very favorable effects. I mean, not as much as the rodents. It's very difficult to have the exact same amazing effects in rodents as it is in humans. But the fact that you're seeing translational effects, which almost I mean, it almost never occurs with, you know, typical supplements and pharmaceuticals, but we're seeing these promising effects in humans. And then with that Harvard study, for example, now they're actually have obtained approval from the FDA as a investigative new drug to do similar type of research during extracorporeal blood circulation, to actually do use hydrogen gas during this period as well. So this is an ongoing thing that appears to just continue growing with more research groups from different places looking at it more. And initially, again, that hydroxyl radical is it is a very major contributor to the damaging effects that occur during ischemic perfusion. And that's why almost every article, especially the earlier articles that you look at on hydrogen gas, it talks about the hydroxyl radicals and a major emphasis on the ischemic perfusion. But as we were talking about, well, maybe the hydroxyl radical is not as biologically significant, that the scavenging activity of the hydroxyl radical is not as biologically significant as we thought it was before.
Well, and at least in individuals who aren't dying acutely from some severe stressor.
Right. Yeah, exactly. Yeah.
So normal humans.
Yeah, those who don't have a huge bout of hydroxyl radicals that have already oxidized all the antioxidants and everything else already, right? Mm-hmm. But the fact is that when you do the chemical kinetics, and I've done quite a bit of math and things on this, looking at the second order rate constants, and you know, the fact is hydrogen gas to react with the hydroxyl radical is about 3 times the rate constant about 3 times lower, orders of magnitude lower than it is for other nucleophilic molecules that would react with the hydroxyl radical. And so when you just do some of these calculations, you start seeing that despite hydrogen gas being able to diffuse very quickly and have, you know, and get to these places very easily, the hydroxyl radical just reacts so fast that the probability, just based on probability, for it to actually interact and intersect with each other is quite low. So something else has to be going on. And in fact, even with these ischemic perfusion studies, if we were to administer hydrogen gas, say, you know, the hours before, and then hydrogen gas is only going to stay in the body for, say, an hour, okay? And then after all the hydrogen gas is gone out of the body, and then and then there's an ischemic perfusion attack, an IR, ischemic perfusion IR injury, you still see a very pronounced benefit from previously administering hydrogen gas, despite the fact that there was no hydrogen gas present in order to scavenge these hydroxyl radicals. So how do you explain that then, right? So this is why it's a recognition that hydrogen gas is clearly, its role is much more than just acting as this typical antioxidant, but truly acting as a gaseous signal modulator that is able to, you know, influence gene expression, protein phosphorylations, signal transduction cascades, all of these things that help explain the therapeutic effects we're observing from hydrogen gas.
Yeah, and is that primarily done through the NRF2 pathway?
I would say yes. Yeah, so the antioxidant effects of hydrogen gas is probably one of the main things. So yeah, we should probably talk about the NRF2. Again, the NRF2 is this protein that's bound. It's in the cytosol. It's bound to another protein, KEAP1. And when there's an assault of oxidative stress or something, then those two separate, and then the NRF2 is able to diffuse into the nucleus of the DNA, and it binds to the electrophile response or AR, the antioxidant response element portion of the DNA. And when it does that, that ends up leading to the production of a whole bunch of endogenous antioxidants like your glutathione, superoxidase mutase, catalase. In fact, the NRF2 regulates and controls over 200 cytoprotective proteins and enzymes. That's why it's called phase 2 detoxification enzymes. So when we talk about antioxidation and detoxification and all this stuff, a lot of that is all regulated and controlled by NRF2. That is the master regulator. So it is a key protein involved in all of these cellular processes. And it turns out hydrogen gas is able to activate the NRF2 pathway.
Now, how would you compare it to some of the xenohormetic activators of NRF2, like sulforaphane, which would be, I think, classically considered one of the most powerful activators?
Yeah, well, I guess for me, I wouldn't compare it because it's
like, okay.
You can take, you can do one study and you can directly compare the two, but that's looking at, the cell culture or something. That's not going to give you the indication of what's really going on, because the pharmacology of the two were totally different. Hydrogen gas, in fact, hydrogen gas may not, if the cell is already normal and it already has the correct cellular homeostasis, and there's not an excess amount of oxidative stress going on, you might find that there's no actual increase in NRF in downstream NRF2 proteins that have been activated, because you already have normal levels of, say, superoxidase mutase or catalase. You don't want to have higher levels. You might see increases in mRNA production of NRF2, but just because you see higher mRNA, so mRNA is the messenger RNA. So you have to have your DNA, and then you make mRNA, and then mRNA is used to then make the proteins. And so it has to go through this process. So you can have an increase in mRNA, but just because you have an increase in mRNA does not necessarily mean you're going to have an increase in proteins. And so sometimes hydrogen gas increases the mRNA levels, but that doesn't always mean that, well, a lot of things, not just hydrogen gas, but just because the higher mRNA levels does not mean you're going to have higher protein levels, and because those are further regulated. And so the point is, whereas with sulforaphane or some other things, you'll almost always see a spike and increase in the NRF2 production, where with hydrogen gas, you may not necessarily see that because it may not be needed.
So that's the primary distinction, is that there is no endogenous feedback with sulforaphane. It's just pressing the accelerator on NRF2 indiscriminately, whereas NRF2, you've got this endogenous control system that only produces it if it's necessary.
Yeah, that's probably a good way to think about it, and that's one of the nice things about hydrogen gas that really decreases its risk for being toxic to the cells, because it doesn't have the capacity to just go in indiscriminately and just force the production or induction or something of the NRF2 or a whole bunch of other molecules that it's able to regulate. It tends to bring things back to homeostasis, and the further something is away from homeostasis, the higher the probability that hydrogen gas will be able to help bring that back into homeostasis. But if something is already at a perfect level, well, then you may see that hydrogen gas didn't do anything for that to maintain that perfect level.
And why don't you have a few other comments on the safety profile? It appears to be one of the safest therapeutic options that's available to humans, and the toxicity is almost non-existent. So why don't you give a few examples that support that supposition?
Yeah, absolutely. So one of the things about hydrogen gas, because it's not just such a strong pharmacological agent, that means that it's not going to, it's not like an NSAID, a non-steroidal anti-inflammatory, or a steroid or something where you can have this dramatic effect. And things that have dramatic biological effects often are going to have very toxic effects when taken too much or too high. And the smaller the effect, the less likely it is to have a toxic type effect. Although anecdotally, there are people, when they take the molecular hydrogen, they notice a very quick relief of, say, pain or different things, which you can talk about that later. But the fact that hydrogen gas is a very mild molecule that tends to regulate things back towards homeostasis helps it to be a safer molecule. And so when we look at the studies done on molecular hydrogen, we can see the safety from several different angles. Number one, if we look at research from deep sea diving. So in deep sea diving, typically they use, often they use helium gas, because it's not very narcotic compared to nitrogen gas. But when they go really deep, sometimes they'll even use hydrogen gas, like hydrolix or hydroxy even, which is like 98% hydrogen gas, and they go very deep because hydrogen gas is less narcotic than any other gas. And these pressures we're talking about are extreme pressures that there's no way you could ever, I mean, we're talking about 10, 20 atmospheres of pressure.
Wow.
And they've done these studies, and these human studies, with 19 ATM atmospheres of pressure, and and the balanced oxygen. So there's actually still the same amount of oxygen available on a mole basis.
God, they'd have to do it hydrogen, because the oxygen toxicity at that pressure is just enormous. You'd go into a seizure and die.
Yeah, exactly. Yeah, so they have to lower it down to so there's the same amount of molecules in that under that pressure, right? So, but when they do these studies, there's no long toxic effects of the hydrogen gas. So, despite the fact that you're at very high pressures, we don't see any long-term toxic effects. And interestingly, there's some of these people who've been doing deep sea diving for a long time. When you go down there really deep, you get this this deep sea diver type anxiety, this kind of a sickness, you know, where you start being quite scared, basically. And hydrogen gas also has this biological effect to slightly suppress that anxiety, so that you can think better and be more calm and be clear. And so it has this other effect that deep sea divers have known for a long time, never really understanding why, and maybe we're understanding a little bit more because now we understand the biological effects of hydrogen gas. So the first line of safety simply comes even from the studies that have done since the 1940s in deep sea diving. Then we have the other studies. Well, actually, another big one is the fact that hydrogen gas is a natural molecule to our body. It's not some alien or foreign substance that our body's never been exposed to. We're exposed to hydrogen gas on a daily basis from the bacteria in our intestines that are producing it all the time. So we're always exposed to hydrogen gas. So when you eat your fibers, your non-digestible carbohydrates, your fruits and your vegetables, a lot of that fiber can then be metabolized by the bacteria in your intestines to produce hydrogen gas. And then you end up having hydrogen gas in your blood and in your breath. And there's quite a few studies demonstrating that this hydrogen gas is indeed therapeutic, and it has therapeutic effects. And by blocking the production of hydrogen gas, despite still giving fiber, a lot of those benefits are eliminated or at least significantly reduced. In fact, some of them have been suggested that some of the drugs like acarbose or different things that have cardiovascular protective effects may have something to do with the fact that more hydrogen gas is being produced. So again, about the safety of deep sea diving, you have the endogenous production from the body, and then you have the actual studies that we've been conducting whether in animal human clinical studies or in animal studies or in the cell culture studies, where we've taken at a cellular level, taken the concentration of hydrogen gas, to, let's see, if it's 20 micromolar, so 10 times, 100 times higher than you'd ever get by taking hydrogen gas any other way. And we see in the cells that there's no toxic effect. And so this is a very big issue, a benefit with the safety of hydrogen. Now, one interesting thing though is maybe hydrogen gas does have a toxic effect, and that's why it induces this hormesis effect. Because how does hydrogen gas activate the NRF2 pathway? In order for hydrogen gas to activate NRF2 pathway, it has to be doing something that causes the cell to be like, wait, something's not quite right. I don't know what it is, but I'm just going to activate these cytoprotective proteins just in case. So hydrogen is doing something. But when you look at the study, so for example, in one study, they administered hydrogen peroxide to the cells, and that both can kill the cells as well as it can activate the NRF2 pathway. When you administer the hydrogen gas with the hydrogen peroxide, the cell survival increases because hydrogen gas is protecting. And so it's not that hydrogen, so somehow if hydrogen gas were just indiscriminately activated in the NRF2 pathway, then you would actually see that if you administer hydrogen peroxide, a toxin, and then you administer hydrogen gas, which also would ostensibly be a toxin because it can activate the NRF2 pathway, then you would expect to see more cell death. But that's not what you see. You see an increased cell survival. And then when you administer hydrogen gas alone, without the hydrogen peroxide, you can still see an increase in the NRF2 pathway. So again, hydrogen gas has this dual role where it can both protect against the oxidative distress as well as act as this mild hormetic effector in the mitochondria to increase mild amounts of free radicals, similar to an easy bout of exercise, for example, which can then induce these protective effects. So there might be a toxic effect, but it's so small and for such a short amount of time that is what mediates the benefits of hydrogen. And then by the time you build up hydrogen and everything else, you never actually get a really toxic effect of hydrogen. Because the fact is, hydrogen gas does not build up in the body. You just expel it out. It's gone within an hour after ingestion.
And we'll talk about the dosing next. I just want to make a comment first and repeat what I think a comment I made in the first interview that we had, which was an experience I had during my residency program, which was in an inner city hospital. And there were many end-stage alcoholics there, and a number of whom had hepatic encephalopathy. Essentially, because their liver was shot, they were in a brain coma. And one of the treatments at that time, and I think still may exist, I haven't practiced that type of medicine for many decades now, but was lactulose, which is a non-digestible carbohydrate, which is fermented by the bacteria. At the time, I didn't know this, but it was fermented. And I don't think anyone knew how it worked, but it worked. I mean, you give these patients lactulose and they would come out of the coma, but it appears to generate increased hydrogen gas production by the bacteria in the gut because it's fermented by them, and boom, activates NRF2 pathway and they're rescued. It's just extraordinary and a simple, inexpensive, non-toxic solution.
Yeah. Thanks for bringing that up. Yeah, lactulose is a great, it really does increase the production of hydrogen a lot. And there are specific studies that have been done using lactulose showing the benefits are mediated by hydrogen gas, but we don't understand if that's all of them.
Yeah. So but ultimately it's this hydrogen gas. So people might be wondering if they're not familiar already, how do you get hydrogen gas? There's the obvious ways are that you can inhale it. And as you mentioned, they're doing this in many studies in Japan to see if the benefits, but that has its downsides because you can talk about how it's administered from inhalation, but it's not easy and it's not simple and there's a lot of complexity to it. And the other way is to dissolve that gas in water and drink it, which is a lot easier to do through a tablet mechanism. And of course, you can make it with the electrolysis machines, which are a lot more expensive and don't produce anywhere near the concentrations that you would require. So I think, why don't you discuss those? And then also the really crucial concept here that needs to be understood at a very deep level, in that it's not just, it's counterintuitive because you would think the more hydrogen gas, the better, but that's not the case. Because as you mentioned, we're making like 10 liters of hydrogen gas a day. That's a lot of hydrogen gas, but it's not the absolute quantity that's important. It's the pulsing or the acute elevation over a short period of time that seems to stimulate the NRF2 pathway. So help us understand that at a deeper level.
Yeah, sure. So, okay, so I guess we'll focus on that intermittent type exposure and the dosing.
Yeah, and the gas and the different ways, comparing the inhaled gas to the tablets.
Okay, maybe we'll just go through that then. Okay, so yeah, with inhalation, yeah, absolutely. When it comes to medical gases, typically we're used to administering a gas through inhalation, and it seems almost strange to take the gas and then dissolve it into water and then drink it like oxygen. Like that's one of the biggest scams in the industry in the world.
Oxygen water.
Oxygen water, yeah. Taking oxygen, dissolving the water, and thinking if you drink that, you're going to get all these benefits.
It's not going to work, folks.
It doesn't. Yeah, it doesn't work. There's the low solubility. You have, the oxygen has to be is absorbed in the lungs because that's where the high pH with the Bohr effect and it's all this other kind of stuff.
And it binds the hemoglobin. It doesn't dissolve in plasma spontaneously unless you already have a hyperbaric chamber.
Yeah, which is different, exactly. Yeah, I mean, but the fact is, you would get more oxygen in your body by breathing, an extra quarter of a breath, if you will, in a couple minutes than you would by drinking, water. Exactly. It doesn't work. So it really kind of is strange when we're saying, yeah, you can take hydrogen gas, also a gas, and dissolve it in the water and drink it and get benefits. What's the difference? Because, if oxygen, you can't do it with oxygen, then how are you doing it with hydrogen? Hydrogen also, it doesn't have high solubility. In fact, the solubility is only 1.6 milligrams per liter. So it's like only, that's not very much. Like how can this even work? But the fact is, it does work, and we'll explain some differences between oxygen and hydrogen, and why the hydrogen method in water would work, whereas the oxygen would not work. Of course, so with inhalation, yeah, the studies are very favorable when it's coming to using inhalation. But it's interesting in like a Parkinson's disease animal model where they used inhalation of hydrogen gas 24/7. So 24/7 exposure. The cages were exposed to hydrogen gas with 24/7, about a 2 to 3% hydrogen concentration. And then
this is just as an aside. This is because over 4% it becomes explosive.
correct. Yeah, exactly. Yeah. And the research shows, and that's one of the great things about hydrogen. Even at a level below the flammability level is sufficient to be therapeutic, right? So yeah, they had it, 2 to 3%, and then they had another group that they inhaled hydrogen gas intermittently, so once every hour, okay, for a few minutes, 15 minutes. And then another group actually was given lactulose, okay, which produces a lot of the hydrogen gas. And then the third group drank hydrogen water. And at the end of the study, in this
Were they drinking the water continuously?
just normally, ad libitum,
Okay.
whenever they drink,
Ad
whenever
libitum.
they drink water. Yeah, exactly.
How do they keep it dissolved in the water though? Because it diffuses out pretty quickly.
You just have to, yeah, you just have to change it several times a day.
Okay.
At least change it at least twice a day, and it's also special the way they did it with aluminum foil and decreasing the headspace. There's different ways that the researchers have been able to keep a high enough concentration by the time they change it the next time that the loss is not too great, right? But what they found though was that the continuous hydrogen administration, so 24/7, you're getting the most hydrogen because you've always been exposed to it, right? Had no effect. There was no benefit.
Totally counterintuitive.
Yeah, because you think like, and especially if we talk about the scavenging hydroxyl radicals, well then, if hydrogen gas is always there, always present, you'd be able to scavenge, whatever radical, boom, it's gone, and there was no benefit. Okay. Then when they did intermittent exposure of hydrogen, so intermittent inhalation, there was a benefit, statistically significant, but not fantastic. And then with the lactulose administration, actually there was no benefit either. So
because it's continuous, same thing.
Yeah, probably because it was continuous. Now, other studies, like I said, there are other studies showing that lactulose administration producing the hydrogen gas did exert very therapeutic effects. So there's different disease models, and this was a Parkinson's disease model, and in this case, it did not have benefit. Now, despite that the intermittent inhalation was beneficial, it was nowhere near as beneficial as the drinking of hydrogen water. Okay. So we do see that obviously drinking hydrogen water has its place, and in some cases it could be more effective than inhalation. Now, and then again, that still has to beg the question, well, yeah, but hydrogen gas in water, that's the same problem with oxygen. What's the difference? How in the heck can you have hydrogen water work, but oxygen water does not work? And that's because it's an apple to orange comparison. In order for oxygen, you have to get, we actually literally use oxygen, and quite a bit of it. The atmosphere is 21% oxygen, and we use at least 5% of that every single time that we breathe, which actually is not a lot, but we use about 5% of the oxygen per breath that you take in, but you're actually using this, and it's transported by hemoglobin and all this kind of stuff. Well, hydrogen gas, when you drink it, there's a couple things to consider. Number one, yes, 1.6 milligrams per liter as a solubility doesn't sound very much, because you're like, hey, I'd take 100 milligrams of vitamin C. So 1.6 milligrams, how can that be very much? But don't forget that hydrogen gas is the lightest molecule in the universe, okay? So, of course, 1.6 milligrams doesn't weigh very much, because it's hydrogen gas. Of course it doesn't weigh very much, but it's actually a lot of molecules. In fact, there are more molecules in 1.6 milligrams of hydrogen than there are molecules of vitamin C in a 100 milligram dose. So
that's a very good point. Thank you for helping us understand that.
Yeah. I have to compare molecules to molecules, or moles to moles, not just weight to weight. What weighs more, a pound of gold or a pound of feathers, right?
Yeah, they weigh the same.
They weigh the same, right? So, but intuitively we're like, of course the gold's going to weigh more. Well, it's a pound.
Denser. It's denser.
Exactly. Yeah. So when we look at molecular hydrogen, there is actually quite a bit, and the fact is that there are many molecules that work in the body, biologically relevant concentrations in the nanograms, only taking the nanogram levels. So actually, 1.6 milligrams is plenty. Now get this, when you inhale, say a 3% hydrogen gas, then that's going to increase the cellular concentration to a certain level, okay? Mm-hmm. Now that exact same level, if we can calculate it based on Henry's law and the dose you're getting, the dose you're ingesting from drinking hydrogen water, that concentration in the cells can also be reached by just drinking hydrogen water, because you drink all of it at once and it goes into the body and immediately increases the cellular concentration to the same level that you would get if you were inhaling hydrogen gas at the 2 to 3% level. So it of course, it's not going to be there as long as when you're inhaling, you're typically inhaling for a longer period of time. In fact, we did do a study in Parkinson's disease where in humans, where we tried to mimic the temporal profile of hydrogen gas in the body, and it was a short study, but they only inhaled a very small amount, a very small percentage of hydrogen gas for, I think it was 10 minutes, because they're trying to just mimic more closely mimic the amount of hydrogen gas you would be getting if you were to drink hydrogen water. And we saw two interesting effects. Number one, we saw no statistical benefit. So it doesn't work that way. We didn't see any benefit to the disease model. Maybe if we would have gone longer, we would have seen something, I don't know. But we did see something was happening, because we saw mild increases similar to what you would see with a bout of exercise of oxidative stress. So something was happening. Something in the body was getting to change. So maybe, like I said, maybe if we would have continued doing the study, we would start seeing some benefits with that. But in this case, with the short-term, very small amount of hydrogen, we didn't do it. Now, one of the differences also could be because the benefits of hydrogen gas for the Parkinson's disease, there's some data that suggests that it is partly mediated by ghrelin, which is a hunger hormone, a gastric ghrelin release. Drinking hydrogen water, the oral consumption of hydrogen water, can induce gastric ghrelin release, and then ghrelin acts as a second messenger to benefit the brain. And inhalation of hydrogen gas may not have actually enacted that signaling molecule. So going back to this concept, drinking hydrogen water all at once increases the cellular concentration to the same level as inhaling does for a shorter period of time, right? But it just, boom, right there, you get a very fast concentration. And then you're also able to enact various second messenger systems that maybe you're not getting with inhalation. So there are obviously cases where drinking hydrogen water is more effective than inhalation, and probably vice versa as well. We need more research on that.
Yeah, an important distinction is that you are referencing the normal solubility of hydrogen in water, which is 1.6 milligrams, but there are tablets that create these nanobubbles, which capitalize on Henry's law, and through these pressure differentials are able to increase that concentration to up to 8, 9, 10 milligrams per liter, which is, literally almost 10 times more. So you would expect a better result with a higher concentration over a similar duration.
Yeah, and we kind of some things are kind of suggesting that as well. So we actually used those tablets in some of our clinical studies we did.
You did?
And yeah, so we actually found one of them. We did it with a non-alcoholic fatty liver disease. Okay, maybe we should back up. This is also interesting. We talked about this before, but just to consider about dosing a little bit. Back in 2013, I was contacted by a group who was doing research on alkaline ionized water, and they were trying to look at the benefits of alkaline ionized water on fatty liver disease induced by a high-fat diet. And they found no benefit whatsoever, despite other articles showing the benefit. And I started talking with them. Well, what is the concentration of hydrogen? And they had no idea. They didn't know, because that didn't seem to be an important part in alkaline ionized water research at the time. So I said, okay, we needed to figure out what that is. So I taught them how to measure the concentration of hydrogen, and they were able to do that. They came back, and the concentration was like 0.3 milligrams per liter or so. Then they decided to let's do the study again, the exact same study, but let's do a low dose of hydrogen and a higher dose of hydrogen. So the lower dose, again, about 0.3 milligrams per liter, and the higher dose closer to 1 milligram per liter. So still not even very high, right? That was the ability that we had, again, many years ago to make the hydrogen water for the rodents. Now, what they found is that the low dose, again, had no benefit. There was no benefit compared to just normal control, normal tap water. It was the same as the alkaline ionized water, right? So despite having the negative ORP that they talk about, the alkaline pH, all this kind of stuff, there was no benefit. But the group that had the higher amount of hydrogen gas, and it was a neutral pH, or closer to neutral. You know, I have to look at that study again. Let's see. I think it's actually slightly alkaline because the way we made it. But anyway, it was the hydrogen gas, and it exerted a very prominent effect on the non-alcoholic fatty liver disease. So when we do that, the dosing conversion, because mice drink a lot of water. In fact, they drink, you know, it's the human equivalence for, you know, we'd be drinking, you know, 10, 12 liters a day of water if we were mice. And so all the water that mice are drinking is hydrogen water. And so if you know, so with us, if we're only drinking, say, you know, half a liter or a liter of hydrogen water, well, then we're getting, you know, 10 times a lower total dose of hydrogen. Does that make sense?
Mm-hmm. Sure.
So with this clinical study that we published for non-alcoholic fatty liver disease, and we used some nuclear magnetic resonance imaging technology to look at the fat deposits in the liver and things. We used the hydrogen producing tablets at high concentrations,
Like
and found
9 or 10 milligrams.
Yeah, exactly. Yeah, the same ones. And we found it was a very short study, only 12. Yeah, I think we had 12 subjects. But it was very, very obvious that hydrogen was having an effect even at with these subjects. So again, suggesting this higher concentration of hydrogen. And now I'm just there's another article that should be published shortly. But I'll mention briefly on metabolic syndrome. Most studies have used a rather low dose of hydrogen. Okay, so a milligram of hydrogen per liter, drinking, say, a liter of water. And then in this case, we decided to increase the dosage at the very high levels, you know, using the hydrogen producing tablets. And we had 60 subjects, and we went for 24 weeks, so 6 months long study. And it appears that we had some very prominent effects, and even more effective compared to the previous studies, leading to this trend that, at least in some cases, a higher dose or higher concentration of hydrogen is more effective than the lower dose or lower concentrations. And that should make sense when we consider the very favorable effects we see in animal studies. Well, one of the issues is the animals are getting 10 times more hydrogen total because they're drinking so much more water than we are.
Okay, so thank you for sharing that, helping us understand that the quantity does make a difference if it's done strategically in pulsed and cycles. So it's very clear that a higher dose seems to work better, but the real second essential and important question is, what is the dosing? What is the cycling? Is it once a day? Is it twice a day? Is it once every other day? I mean, how long of a rest do you need before you take the next dose to still get optimal benefits?
Yeah, I don't know. We need to figure that out, because the fact is, like I said, the hydrogen is going to be gone in the body within an hour. Okay.
Yeah.
So it is possible. That's possible. What you could drink hydrogen water, let's say, well, every hour, and by doing that, you would spike and it would go back down, spike and go back down, and maybe that would be more effective, or maybe that would be less effective than drinking it just, you know, once or twice. You only get the spike, you know, once or twice a day. We really need more research on that. But I will say, let's do some other comparisons, right? So let's say you're going to take a total of 10 milligrams of hydrogen. Okay. Now you can
hefty dose.
Yeah, actually, let's say 6 milligrams of hydrogen, because I want to use a different analogy. 6 milligrams of hydrogen, and you're going to take all 6 milligrams evenly in a 24-hour period, right? So that means you're essentially sipping on hydrogen water. Exactly. Yes, that's what you're doing, right? So you're sipping on hydrogen throughout the day. Now, if you do that, you may not get as good of benefits because you're not getting a high enough dose of hydrogen in the body in order to reach the cellular concentrations required in order to induce those benefits and those changes in this at the cellular level that we require, that we need. And now, if in contrast, if you were to just take all that dose, the full 6 milligrams all at once, that is probably going to be more effective taking it all at once than taking it throughout the entire day. And so I would say if you are going to get hydrogen and try to get the benefits, then you would want to get as high of a dose as you can all at once. And then you could probably do that multiple times a day, I imagine. So if you're, like I said, I don't know if it's better to take it just once a day. Let's say take 6 or 10 milligrams of hydrogen once a day. Is that better than taking 6 or 10 milligrams, 6 times a day? Maybe the 6 or 10 times a day is going to be more effective or just as effective, because you're still getting at a high enough level, you're still getting spikes, you're still getting all those different things. But then again, maybe not.
Well,
so,
someone's got to do the darn studies. But in the interim, until then, it would seem that customizing the dose to your personal circumstances might be more appropriate. So that if you're in a normal, non-stressful circumstance at home, not really doing anything very stressful, not exercising much at all, then maybe once a day is sufficient. But if you're a madman like you are with your exercise, then you're going to want to take it to help reduce the oxidative stress from your intense exercise. Or if you're traveling and exposing yourself to free radical stress from ionizing radiation at 35,000 feet, then it might be more appropriate to take it every 2 hours while you're flying. What do you think about that strategy?
I like the strategy of the fact that, try it out. I mean, there are, because hydrogen gas alone is really quite safe, then you're free to really take quite a bit of it at different times to see, the effects from that. I mean, yeah, you might try multiple times a day for a little bit, and then maybe just try it once a day for a while. Like maybe just taking one. I guess when we're talking about the tablets, because there's other hydrogen waters out there. You just have to make sure you're getting the right dose. But at least with like the tablets, that just by taking one tablet, you're getting at least as much hydrogen gas as used in the majority of clinical studies. So now that's like the daily maintenance. And then if you're going to fly, like you said, or you're going to push up really hard to exercise, or maybe you're battling with some sort of condition, maybe, I suppose, yeah, you can, because hydrogen is safe, you could, bump it up a little bit more.
Yeah, the other benefit too with oxidative stress I neglected to mention is that the mechanism these tablets are able to produce hydrogen is it actually use a very pure grade of metallic magnesium. And the magnesium dissociates into magnesium ions. It's not a compound. It's not bound to anything. So it's absorbed very readily, and it's not insignificant quantities. It's like 80 milligrams of elemental ionic magnesium, which is basically 20% of the RDA. So that's a very significant dose. And if you're taking 4 or 5 of them, I mean, you're going to get a massive dose with virtually no risk of loose stools, because it's an ion and you're not going to cause an osmotic diarrhea.
Yeah, that is one of the nice benefits. Most people are deficient in magnesium anyways, and taking 80
So it's a huge benefit, and you're not getting that benefit if you're getting it from the water generators, which are typically they're about 1 milli. I mean, you can't really go higher than the normal solubility of molecular hydrogen in water, which is 1.6 milligrams per liter, right?
Well, it depends. There are some that can get relatively high concentrations. It's just they're hit and miss, and then you have issues with the electrodes. Remember, when that water comes in contact with the electrodes, I mean, hopefully the electrodes are very good, platinum coated, which is very inert. You're not going to have a problem. But I was in China a few months ago at one of the symposiums, and some people did an analysis showing that on some of these units, they had various electrode degradation, causing heavy metals to be leached into the water. Your cadmium, your lead, your arsenic, different things that can be toxic. And so you just have to be cautious about all these types of things.
Yeah, so that's not an issue with the tablets. It's the simplest, the easiest, and it seems like the no-brainer solution. So yeah, that's a good way to do that. So tablets are what I personally prefer. And as I said, it's my favorite. It's my absolute favorite supplementation for all the reasons you just described. So I think we've done a good summary. And what I'd like to do now is transition. Maybe you've shared most of the studies you want to, but I know you're engaged in a lot of cutting edge research. A part of the intention of this conversation was to get us up to date on the newest and most exciting developments in the molecular hydrogens field. So perhaps you can enlighten us.
Yeah, there are some really exciting things that are going on. Unfortunately, some of them are not. We haven't published some of the results yet, and so some things are still. We have to just be cautious on things that we talk about. But I did mention the fact that Harvard University has moving forward with getting ready to do some clinical trials, and that'll be really exciting. There's some other universities here in the U.S. that are doing some really neat studies as well. Actually, I think some of them are actually using the hydrogen producing tablets as well. So
are the Harvard trials on the ischemia reperfusion?
Yeah, using extracorporeal blood circulation.
Oh, perfect.
Yeah.
For heart bypass surgery.
Or other types of conditions. So that's really important to understand hydrogen gas. Now I'm excited. We did a study with showing the effects of, well, we've done these studies before with the radiation protection in rats, where we irradiate the mediasternal area of the rat myocardium, which often can kill the rats, sadly, but cause a lot of necrosis and damage and different things. And drinking hydrogen water is able to suppress that damage significantly, decreasing markers of oxidative stress like MDA, inflammation, tumor necrosis factor alpha, a lot of different things. But this time what we did is we did a protein microarray analysis, which is really going to be very fascinating. We're analyzing the results right now. So typically there's a lot of RNA analysis you can do, where you administer the hydrogen or different things, and then you can look to see what types of mRNA changes were made. Now, the problem, and I mentioned this earlier, is just because you see changes in the mRNA levels does not necessarily mean you're going to actually have changes in the protein levels. And typically it's very difficult to measure.
And for those who aren't followers, the protein levels are the actual endogenous antioxidants that your body's producing.
Yeah, exactly. Those are the actual proteins, the actual molecules that we need to change signal transduction, to do things. The mRNA, although mRNA has a lot of benefits too. MicroRNA, for example, can regulate post-translation and things of other things. But when you measure protein levels, we typically use, say, like a Western blot analysis, which can be quite time intensive, very difficult. Maybe you can only do a few proteins at a time. It's very difficult. Well, we did a protein microarray analysis, and after hydrogen administration, and I mean, when you look at the data, it's just overwhelming. We looked at there's hundreds and hundreds of proteins that were influenced and changed by hydrogen administration. Not a whole lot maybe, but they were changed, and you can see the difference. And in fact, one of the main people who does this, the experts in this field, he was like, I don't know if I've ever seen something as dramatic as all of these changes that are made. So we're very excited to analyze and understand. I mean, they use antibodies, and they have to look exactly at phosphorylated levels of proteins, because that's the thing. It's not just whether a protein was changed, it's about the phosphorylation of the protein, because the phosphorylation of a protein is what's going to have it be active or not active. And it depends, of course, on which amino acid residue it's phosphorylated at. And that's going to dictate whether or not, whether it's activating, inhibitory, or neutral. And so we're analyzing that data right now, and that's going to really help us understand the molecular mechanisms, because the two main things that we really need to understand is, number one, of course, the actual clinical benefits of hydrogen. Like we're seeing a lot of great preclinical and clinical studies that are very promising, a lot of anecdotal reports, but we still haven't, proven beyond a shadow of a doubt, if you will, that hydrogen gas is truly this wonder miracle, that it appears from, say, the animal studies, or people report. We don't know. That takes years and years and lots of research. We do know it's safe, and that's why it's exciting to just keep on studying and to see if it really is, reaches that criteria of being a mainstream medicine, right? But then, besides the clinical effects of hydrogen, is really to understand the molecular mechanisms of primary targets of hydrogen gas. And so this work that I'm involved in right now, it's overwhelming amount of data to try to understand. And this could really help us get an understanding of how hydrogen gas is working, because although there are hundreds of molecules and proteins that are being changed, many of those are just passenger molecules that were changed by upstream molecules and drivers. And so we have to look earlier and earlier on in order to see what was the first molecule that was changed, in order to induce this cascade of other events and changes in protein phosphorylations and altering signal transduction.
So is this yet to be published study is going to be the one that reveals the mechanism of actually how hydrogen gas works? Or at least suggest the mechanism?
Yeah, I think we're getting closer. This specific study is not the one that I had talked to you earlier about, where we think we can see where hydrogen gas can act very, very early on and interacting with part of the cell, and I'm being vague on purpose.
Yeah, right.
But
you have to be, because you can't disclose it because it's not published yet.
Yeah, exactly. And frankly, we're not positive. We need to just do more research on this. But it does make sense. If we're right, then we can see this could happen, and this can cause this cascade of events. It goes right along with our hypothesis on the hormesis effect, and that can be responsible for inducing all these proteins, including the heat shock proteins. We know that hydrogen administration induces heat shock proteins and upregulates the mitochondrial unfolded protein response. All of this is about hormesis, and we can see some things very early on that hydrogen may be doing they're responsible for these, and then we see all these downstream effects of molecular hydrogen.
Yeah, so one of the reasons why I'm so fond of you is not only are you brilliant, as anyone who's listened to this point can really identify this, but you're also really committed to athletic fitness. You're one of the most fit people I know, and really push the boundaries of health. So in that process, and in seeking to optimize physical health, frequently there's benefit to stacking modalities. So obviously molecular hydrogen is something you embrace and engage in. I'm wondering some of the other benefits. So it would seem there would be a benefit for but applying these approaches synergistically together. So I can think of several that I'd like you maybe to comment on. One would be the sauna with the administration of heat shock proteins, which you alluded to, and either the creation of ketones naturally through nutritional ketosis or exogenous ketones, and then what was the last one? Oh, hyperbaric oxygen therapy.
Yeah. Okay. So when it comes to the sauna, I think that's great.
So would you do it together? I mean, would you from what you know of the mechanism at this point, would you do the hydrogen before the sauna or after?
Yeah, I would probably I probably would do the hydrogen before anything. That's like one of the first things I would do. I say I would because I don't always do it.
But at least in theory.
Yeah, at least in theory. Again, it's talking about this preconditioning hydrogen effect. If I can just back up and talk about one study that you'll find very interesting, and I think helps set the stage as well, about NAD plus and NADH. Of course, those are, you've done books and all this stuff on this. These are very important molecules, and the higher the ratio of the NAD plus to NADH, the better. And that ratio, not only the ratio, but also the concentration of the molecules themselves tends to decrease with aging. And in this one very interesting study, they used a toxin in a cell culture study and administered the toxin to cell cultures, and as would be expected, that ratio decreased of the NAD plus NADH ratio. and that ends up having all these, pathological and dead problems and cell death. When you administered the hydrogen gas, it helped to maintain those levels up higher. Now, this is part of the interesting part of the study is they just did it in cell culture. So you can imagine in this little petri dish, you add hydrogen gas in there. Well, that hydrogen gas is only going to be in there for 20 minutes or half an hour, 40 minutes. It depends on the concentration. It's not going to be in there for very long. And they found that there was a therapeutic protective effect against that toxin for about 24 hours. It was able to maintain that effect. Okay, so
that's suggesting a once-a-day dosing may be a possibility. It's certainly not,
or at least a minimum that you should be doing. Right, take it once a day. But see, then the other studies, it's like another mesenchymal stem cells. I believe they went after administering hydrogen for several, maybe it was a week or so long. Then there was still a protective effect for several days later. And then if you want to really go into it, there was the clinical study on rheumatoid arthritis where they had it for 4 weeks, high dose hydrogen water. And after 4 weeks, there was still a protective effect of molecular hydrogen. There were still decreases in the disease rating score and oxidative stress, even after 4 weeks. So you really had an effect on gene expression, epigenetics, signal modulation, something very much more is going on here than, again, just the radical scavenging activity. So, it does appear to slowly but surely, improving, I don't know if improving is the right word, and influencing that gene expression in a favorable way. So maybe improving is okay. So taking this together, when we look at other things such as the sauna really is quite a mild thing. I don't know of, I suppose there's probably some toxic effects from a sauna, especially if you're in there for too long, just as a temperature issue and thing. But I still like the idea of taking the hydrogen before. And then when you're talking about your hyperbaric oxygen, then I say I think there's even more rationale of taking the molecular hydrogen before as kind of a pre-treatment, preconditioning.
And before would be at least 30 minutes, maybe an hour, somewhere in that time frame.
Yeah, exactly. I think that would be ideal.
Okay.
And that way, because oxygen, hyperbaric oxygen, you do get a lot of those benefits, but you do increase oxidative stress. You have different things going on. And of course, a lot of that is what mediates some of the upregulation of DNA repair enzymes and NRF2 we talked about and other things going on. But hydrogen can help to mitigate some of the...
So the sauna and the hyperbaric are also hormetic stressors, like we believe the molecular hydrogen is, but ketosis doesn't appear to be hormetic stressor. It's an alternative pathway. It's an alternative nutrient, actually. It may be source of calories that these water soluble fatty acids that go in there and have enormous benefits. There are HDAC inhibitors, histone deacetylase inhibitors. They activate not only NRF2 but FOXO3. And they increase NADPH, which is another magnificent way to radically reduce oxidative stressors. So have you looked at any studies using them synergistically? It would seem to be benefit, but I'm just not aware of any that have evaluated that.
Yeah, and I don't know either. That's probably something that should be looked at, and we can look at some of the pathways that hydrogen gas also is able to activate or optimize. I suppose sometimes when it talks about hormesis, some of it is semantics, and in fact, some would even argue that hormesis, that ketones and fasting and all this stuff is also a form of hormesis. It's not as clear the definition of how we as maybe we would like, but some of these pathways that are activated. Is this some of the benefits? So, for example, with the mitochondria, well, those ketones, whether they're endogenous or exogenous, are very beneficial for the mitochondria as long as the mitochondria are ready for them. Their ketones also can increase free radicals, at least initially, depending on the right places. But this is also what's very good because in the long run, they can decrease oxidative stress. You have a better handling efficiency of the metabolism of the ketones. Part of this is why you can upregulate the NRF2 pathway. Well, hydrogen gas being able to both suppress excessive oxidative damage as well as improve and activate the function of the mitochondria, improving the mitochondrial membrane, rest membrane potential, have influence in the mitochondrial transition pores so you don't have pathological problems. That's more for the ischemia, reperfusion issue. Increasing mitochondrial biogenesis itself by increasing PGC1 alpha. So there are some similar areas where ketones seem to work as does hydrogen gas. And then maybe, like in some of the data I'm going through right now, we're seeing some phosphorylated levels of various proteins where ketones also influence, including like AMPK pathway, and a lot of different areas that we can see clearly there are some similar proteins being influenced, but that doesn't necessarily mean it's
so
going
it's increasing AMPK levels. That would suggest it would be beneficial in autophagy too.
Yeah, and in fact, that's yeah, we should. And that's what I'm saying is, just because we see an increase in some of these different proteins doesn't necessarily mean that's the pathway that's going to occur. So, like autophagy, absolutely yes, hydrogen does, and it can induce and actually enhance autophagy. Autophagy is
Wow, I did not know that. That's beautiful.
Yeah. So we can
thing.
see increases like Vesselin-1 levels and in MC2 3 the MC3-1 ratio, the microtubule, which is a autophagy complex, decreased phosphorylations of like a STAT3, the mTOR-C1, all these areas so you can have increased autophagy, and by so doing you're going to get therapeutic protective effects from the hydrogen gas. However, there are other studies showing that hydrogen gas inhibits excessive autophagy. And
excessive autophagy.
Yes, exactly.
Like anything in life, excessive can be bad. So because there's no question you can have too much autophagy.
Yes, exactly. So that's how cells die, right? You have necrosis, you have apoptosis, and you have autophagic cell death. And when you have too much going on, and a lot of drugs or interventions, things can potentially cause an excessive amount of autophagy, then that's bad. Well, hydrogen gas. So for example, what was the compound? There was a drug that was used in the study. I forget, but it induces autophagy too much, and it causes a lot of pathological problems.
Dinitrile something. No. Anyway, I forgot.
Yeah, it's not dinitrophenol, but it does start with. But they was able to prevent the excessive amount of autophagy being produced, and there's even going to talk about mammalian, what's it, mammalian target of rapamycin, mTOR.
Yeah, simple mTOR.
Yeah, but with sometimes, even with this one, maybe hydrogen gas in some cases activates mTOR, which is that's bad, but it's also really good because if you want to get recover and get stronger and all this stuff, you want to mTOR activation. Well, hydrogen gas, it appears in certain cases it could do that. In other cases, you're having lower mTOR. Same thing with IGF-1. So in one as a human study, IGF-1 was decreased by hydrogen. But in another, there was some increases in IGF-1.
And it depends on where this IGF-1 is. Is it in the muscle or is it in the plasma? It has different consequences. So
that's exactly right. And then you have to talk about, okay, what about the receptor? The receptor sensitivity, right, to different things. So there is so many things to consider. Just because, again, a molecule or a hormone or a protein is increased doesn't necessarily mean it's going to have this direct effect. We have to look at the actual outcomes.
That is great. I did not realize it influenced autophagies, because it makes perfect sense, because I'm a big fan of time-restricted eating, in which case, and that's where I do my exercise at the tail end of time-restricted eating. So I haven't been eating for 18, 20 hours, then do the sauna, and then I'll eat a big meal. But it sounds like an hour before to do that whole sequence, doing the hydrogen would not only improve autophagy, but then on the tail end of that, activate mTOR for protein rebuilding muscle protein synthesis.
Yeah, it may. I mean, the jury's out. We need to have tons more studies, but that's kind of the nice thing when you think about maybe people who are doing these long fasting and they're getting a
Mhm.
lot of autophagy. Well, maybe their autophagy stuff is going really good in their brain, but they're getting too much autophagy in their kidney. And this is
Yeah, yeah.
really, it's not that simple. But the idea then is, okay, so if you take hydrogen, then you can continue to enhance this autophagy going on in different areas of the body, but attenuate some of the excessive autophagy going on in other places, and that's
Yeah.
going to make
Boy,
your long-term
that's a
fast safer.
great strategy. I'm going to start recommending that for people who are doing fasting,
You,
longer
you,
fast. It's crazy not to do it. I mean, the cost is so low and the benefits are so high, and there's virtually no harm or
yeah.
danger.
Well, and think about it too. When you take hydrogen, you can increase gastric ghrelin secretion, and ghrelin is the hunger hormone. So one of the first things you do when you fast is you increase ghrelin, and then ghrelin is extremely neuroprotective and anti-inflammatory and a whole bunch of benefits. Well, hydrogen also increases ghrelin. So in a lot of ways, hydrogen mimics fasting. From autophagy to ghrelin to a lot of other pathways that are activated. But it depends on the condition.
Yeah. Yes, indeed. Wow. This is fascinating.
You, you know,
So,
you might consider with some of your fasting and things to actually eat, because you eat and then do the workout. Because if you're always doing it at the tail end of your fasting, you can actually get more benefits by switching that up and actually have your food and then half an hour after that do your hard exercise. And by making those switch,
what's the rationale for that? Help me understand.
because when you're exercising hard like that, you have so some of the studies, for example, how were done with taking your essential amino acids or your protein or different things before your workout, and the utilization of the amino acids and the proteins and everything increased significantly higher by taking it before than by taking it after. And by having higher substrate, so for example, some other studies, when you're exercising, you have low glycogen levels because you've been
Hmm.
fasting. You have your central nervous system, a lot of things are just kind of toned down a little bit. Of course, you're more adapted, so it's not going to be as much, but there's still things that are going on to decrease total efficiency that you could possibly do. And so by having substrate, energy, and fuel and all this stuff in your body before you exercise allows you to have a potentially harder, stronger, and better workout and utilize the nutrients even more. Now, that's only going to work if you're doing this intermittent thing.
I
So
was going to say, yeah, that's the other component. Once or twice a week, maybe.
yeah, or maybe some weeks on, some weeks off. I mean, I don't know what that
Yeah.
that option that
It's an
best thing
interesting,
is.
I'm going to try that because I
Yeah,
do hard workouts with my personal trainer twice a week. So that's a perfect opportunity to do that.
yeah, yeah.
Yeah, I love it. It's great. Woo. Wasn't expecting that benefit. If you provide some compelling uh, evidence and at least stories that strongly support using this, it would seem from my perspective that it's almost medically negligent not to have molecular hydrogen in your cabinet, the tablets, just in case, someone or love, maybe even yourself, has a stroke or a heart attack. This should be one of the very first things that you're doing. And let's go over some of the fine details of the dosing, because the normal dose is 1 tablet, and that at this high dose, if you put it in 500 mLs, a half a liter, which is about what is that, 12 ounces, 16 ounces, 16 ounces, I think.
6 ounces.
Yeah, 16 ounces. You're going to get about 9 to 10 milligrams per liter. So that would be 4 to 5 milligrams that you'll be getting. So, but you can use more than 1 tablet. And I take 4 or 5, 6 tablets sometimes. I don't know what you probably have taken 10 or 20 tablets at once. So why don't you walk us through that and how you would put the tablets in the water, how you'd look. I find that it's important to actually set a timer, because you can't just put the tablet in the water and drink it. It's not going to work. You have to let it dissolve, and the rate at which it dissolves can vary from anywhere from 1 to 2 or 3 minutes, depending on how cold the temperature is of the temperature of the water. If you put it in ice water, it's going to take a long time. But so why don't you walk us through that, and what do you think the tablet range should be?
So yeah, I've talked to the manufacturer,
Alex.
and
Alex?
Alex on
Yeah, I've interviewed him before too.
Oh yeah, that's right. So I mean, he'd probably be better to talk about some of this stuff than I would, but at least from what I've seen, and also when we've done some studies with the gas chromatography to get the highest concentration, it would appear that you probably want to use just your normal room temperature, water, not cold water. Cold water, like you said, does take a long time, and then by the time it dissolves, most of the gas is already gone.
Yeah, and
Because
not sparkling water either, which you educated me on. Because sometimes on a flight, I like to use sparkling water, but not a good idea that it already has CO2 dissolved into it.
yeah, because well, this sparkling water can bring the gas out faster. Yeah. Um, so maybe room temperature water, and then what we instructed some of the subjects to do, for example, is once you put the tablet in there, as soon as that tablet rises to the top of the water, that's when you start drinking it, because by the time you finish drinking it, the tablet has fully dissolved. So at that time, the water is very cloudy and milky and everything. That is the quasi suspended hydrogen gas in there, and you don't want to wait until it's clear, because if you wait, then all the gas is just escaping into the atmosphere. So you don't want that.
You
It's
won't get the
best.
benefit. You're just losing it.
Yeah, exactly. You're losing a very. I think if we did the test, I think you can measure close to 10 milligrams per liter, and then if you wait until the water was clear, you're only down to like 2 milligrams per liter, right? And
That's
so
80% loss.
yeah, it's a pretty big loss. So you're better off drinking the water prematurely and than in swallowing the last fifth of the tablet type thing, because it'll just obviously react from the stomach acids, get all the benefits anyways. You're better off drinking a little bit prematurely than you are waiting too long.
And any comments on the number of tablets, or any concerns they're taking too many?
Just because it is magnesium, right? Obviously the DRI is what 400 or 500 milligrams or so. Most of your supplements are like 200 300 milligrams of magnesium just for a supplement, and a lot of people, I think even you often will recommend maybe 1,000 or 2,000 milligrams of
Yeah.
magnesium.
Especially if you're trying to mitigate against oxidative stress from EMF exposures. Because there's some strong suggestion, no definitive studies that I've seen published, but strong suggestions that magnesium will serve as a calcium channel blocker, which there's some compelling research that suggests that's part of the process that EMFs mitigate or mediate their damage cellularly.
Yeah. So I guess if there's 80 milligrams, maybe don't take 10 every day.
All right. So yeah, maybe 4 or 5, but I think if you have a big exposure for whatever reason, like if you're flying at a high altitude, or if you've gotten a heart attack or a stroke, I think cautions to the wind, and maybe even those are the times where you maybe want to go to 10 and take a really high dose. So, but otherwise, just a few tablets would be.
Yeah, and I agree with you. I do think that it's prevention is better than cure, or sorry, better than
No,
better than cure. Yeah. But
yeah.
I don't want to give any false hope, or I'm excited about hydrogen and everything, but honestly, we don't really know that if you take the tablet and then or hydrogen and then you have a stroke or something, that you're going to be way better off and all this stuff. I don't know that, we don't have the research for that yet, right? And maybe it'll come. Maybe we'll actually maybe we'll discover 5 years from now that actually the biological effects are minimal. But because hydrogen gas is safe, then you need to make, as the consumer, right, the choice. Okay, I have a possibility of it not benefiting me and getting some good magnesium in the case of the tablet, or B, the possibility of actually getting good benefits. I guess I'm just want to say that I am very excited about it. The research is promising, all this stuff, yes, but
we don't have definitive clinical proven studies at this point. Just strong suggestions, especially in animal studies.
Yeah. I mean, it's exciting,
And Harvard is doing the clinical trials now, so we'll know. So that's good. And so, any other studies that you've encountered or wanted to share, or have we covered most of them?
Yeah, I think we've covered most of them. There'll be, I think, by the time we do our maybe a next podcast or something, we'll have some more data that we can we can share. And there's always so much to talk about hydrogen, and just because it really does cover so many different metabolic pathways and signaling. And maybe one of these times we can talk about a specific area or something like this, where hydrogen could come involved or something. There's a lot we could talk about.
Well, this has been great. I want to thank you so much for everything you're doing and you will do. And maybe next time we talk, you're going to get your PhD pretty soon. Do you anticipate to have it this year?
Yeah, I do. I mean, I don't know. It's a lot of work that we're involved with, some publications and some research and things. So it just one step at a time. I mean, nothing's going to change. I always hope that at the end you're gonna somehow learn something because you have a title or something else.
Well, it's nice to give you a little validation. We knew you were the expert and really had the scientific mind, and I so greatly appreciate your support when I'm writing my new strategy now is not to write books, as I've shared previously, and write scientific reviews. And you're like the main primary reviewer I send to first for critical analysis, because you never hesitate to tell me when I'm wrong or I've got this thing mixed up. So I really greatly appreciate that about you.
Well, I appreciate that I'm given the opportunity, and I really appreciate when I do, to give you maybe some criticism or something that you're always just so grateful for. Like, oh man, I'm so glad you told me this. That's really good. I really appreciate that.
Yeah, it's a good collaboration. So really appreciate everything you're doing, and we'll definitely have you on again, maybe by the time you get your PhD. And in the meantime, I would encourage those of you who are listening, if there's been a lot of information shared here, and it would be the rare individual who's not going to benefit from listening to this a second time. I'm going to listen to this a second time. So really, I've gotten some really great insights on how to modify my current protocol. So I thank you so much, Tyler, and really appreciate it again.
Yeah, thank you. And you're welcome to look at my website, Molecular Hydrogen Institute. You're welcome to, add me on social media.
Yeah, what's your social media handle?
So Facebook, just Tyler LeBaron, and I just got an Instagram account recently. I post some stuff, when I'm out doing research. Sometimes I'll post some new articles, but it's a Tyler W. LeBaron. You just look me up, and hopefully I can help spread the word.
Yeah, well, that's what we're trying to do, and you too. So, all right. Well, thank you so much.
Yeah, thank you. Appreciate it.
Thanks so much for watching. Remember, hit the like and subscribe button so you can get more videos that can help you and your family take control of your health.